this class only has a couple of things that will allow us to count how many instructions and dump them into a file. The other important thing in this code is that we have here this register class, which is a C++ way of getting this class to be known to. It's a factory, it's a simple factory design pattern that lets, without having to change the rest of COTSon, if you instantiate it this way, COTSon will allow you to use this anywhere without having to here. So let's go directly to the simulation. The simulation, we'll see a much more complicated CPU timer later. This simulation basically increments the instructions and cycles because this is mandatory. You always have to increase time in some way. You have to, every time you explain instruction, you have to increase the amount of instructions that you've seen, and you also have to increase the amount of cycles every time the time passes, because if not, this would cause a problem inside COTSon. But mainly what we do is we measure a couple of things, and if one particular option was set, we disassemble to a file. Okay, this is another one of the things that can be programmed. Every time that you build a model and use that add syntax, add an instruction and variable instructions, what you're saying is that you're making those metrics, which we call the metrics, visible to the external world. So every time that sample finishes, or every time that you that at specific points in time, all this information is going to be printed out and sent to wherever you want. So let me show you. This is a very simple. We have, besides having the signal commands part that we already saw before, which you select the BSD, you select the HDD, you set the journal, we also send in some keyboard commands. And that keyboard commands is exactly the name of a script that's going to get executed on this particular BSD, which is basically GCC from the spec benchmark. Then we have a couple more things. We have the options table, which is all the main options that you want to give to COTSon. And we have the build function that we'll see shortly. And then we have another function, which is Lua, which is there just for the purposes so that you understand that you can write anything there. So it's not being used a lot just to say where the output files are going to go. But if you wanted to put your own application there, write your own Lua application that is being used for anything, you can put it there. So this gets executed every time that it's needed. So for example, the main thing that we have here in the options is that we're only going to execute one sample. So after one sample, the simulation is going to stop. We're going to use the simple sample, which is always on, which is basically like continuous simulation. The deliver part doesn't really matter right now. And we're going to produce one heartbeat, which is the output, at the end of the simulation, and we're going to write it to that file. Then this function, which is the build, is the one that really builds the model. This is a very simple model because it does have a simple disk, a simple NIC, and the dump to model that we just created. So every CPU gets a dump to model, every NIC gets a simple NIC model, and every disk gets a simple disk model. We'll see more complicated models later. But once this is done, we can basically do the exact same thing as we did before, the bin, COTSon node, input, dump to simple. Or instead of using all these, I've created a script which has been run dump to simple. It basically lets you run all the examples on it. So if you ever get this thing, we can run it. Here we're running non-interactively, so you won't see anything appearing. This is the output. It's very fast. Notice that we are sending keyboard commands and all this. So we here. So here you get the whole output, and you see all the modules being loaded and everything being loaded, and eventually you reach, after loading the BSD and HDD, we translate the keyboard commands that you wanted to send into the real thing that Signal understands. There's always ways of, if you read the Signal documentation, of bypassing our helpers and going directly and sending all those keyboard commands. Eventually, after all these keyword commands, we send it go, and we notice that the simulation is very fast, because eventually when we reach the first simulation sample, it finishes. It determines that it reached its max samples and it finishes. So we're going to see, instead of seeing this output, we're also going to see our own output, which is normally the AA desired term. Here we reproduce all the input commands that you have to send to us and all the output commands. And this is not the most user-friendly kind of output. We have a database output and we have an output that is good to see here. So if you see here, you may see that how many memory loads and how many memory stores we had, because those variables are the ones that the down-to module decided that it was going to track and it was going to export using the add interface. And we also have all the information for the disk and all the other stuff. And we also classify all the instructions based on the branch type of the instruction that they have. This is an example. And yeah, and you can see there's one small thing here that everything that's inside the timer domain is what your timer gave. But outside we got information from what SimNow gave us. And SimNow counted one instruction more than what you got. Because mainly we always leave one instruction there so that we can tell SimNow to continue. So there's some discrepancies there, but it's not very much. Okay, and this is such a simple sampler that it doesn't do anything. Notice that one of the things that we told the dump to is that it could have the capabilities of dumping into a file, that was optional. So if we go here, we say that if this parameter here, say the params file, which has a default of empty, if it's not empty, we're going to assume that you want us to write something to that file and we're going to produce a disassemble. But we didn't pass this parameter, so if we open the next, we have another example with this module, which is the dump to symbol. This file is exactly the same. Well, we changed the name of the log file so that they don't collide, except for the fact that here, for each CPU, we produce a timer that has this extra parameter here. And all these kind of parameters that you pass to your own timers, they don't really need to go. So you can put as many parameters as you want and as many output parameters, as many output variables that you want without having to change anything in constant. So you're basically free to control your input and your output of visual things that you send to your application. So here we produce a file that's called down to disassem, and if instead of running the previous here, if instead of running we run this other new application, it will do exactly the same thing, that now every time that one instruction gets loaded, appears into the timer, it will dump into the file. And let's see, output down to it's this one. So here we have the disassemble of the file. We get if you see the slide, it's more interesting. We get the PAD, the TAD, and the CRF of the particular application that was causing this dump. Currently they're all 0 because we don't get that information until there's a context switch on the application. So, and this is a very sharp simulation. You'll see those numbers later. Then you get the PC. Then we get the length of